So if you've ever touched electronics, you know the starting point. It's always Ohm's law.
Always. V equals IR.
Exactly. It's clean, it's simple. It feels like this fundamental truth of physics. It works perfectly for, a simple light bulb or a space heater.
It does.
Hmm.
It absolutely does for those things. But the moment you look inside your phone or your laptop, that clean, simple relationship just kind of falls apart.
Because it's not so simple in there.
Not at all. Modern circuits are just packed with components that are designed intentionally to be nonlinear. And for those, we have to go deeper than Ohm's law.
Which is really just an observation, an empirical rule.
Right. It's based on experiments.
Mm.
For the real stuff, we need the universal operating system for circuits. Kirchhoff's laws.
And that's our mission for this deep dive. We're going from that handy rule of thumb, V equals IR, to the foundational physical laws Gustav Kirchhoff figured out way back in 1845.
And the key difference, the reason Kirchhoff is so much more powerful, is where the laws come from. Ohm's law, like you said, it's empirical. It just describes what happens in certain materials. Kirchhoff's laws are different. They're direct consequences of the most fundamental laws in physics we have.
Sure.
The conservation of charge and the conservation of energy. Can't break those. And that makes Kirchhoff's laws totally universal for any network, linear or not.
Okay, so let's unpack that. We all lean on V equals IR. When exactly does that perfect relationship start to fail us in the real world?
Well, Ohm's law describes a perfectly linear world. You graph voltage versus current, you get a perfectly straight line.
Double the voltage, double the current, simple.
Exactly. Resistance is constant.
Mm.
And even in AC circuits where we use impedance, Z, and we say V equals IZ, the relationship between the magnitude of the voltage and the current is still linear.
But modern electronics, they need to do clever things. They need to process information. And for that, you need to break that linearity.
You absolutely have to break it, and we do it on purpose. The failure of Ohm's law, it happens in any device that has what we call non-constant transconductance.
Which, in simple terms, means?
It just means the resistance changes depending on the signal you put in. So that VI graph isn't a straight line anymore, it's a curve.
So give us the classic examples. Where does that straight line just completely bend?
The number one example is a diode.
Right.
A diode, or its more complicated cousin, the transistor, they don't have a constant resistance. The current that comes out is an exponential function of the voltage you put in.
And that nonlinearity, that curve, is what lets it work. It's what makes it useful.
That is the entire point. That's what lets a diode act like a one-way valve for electricity. It's what allows a transistor to be a switch or an amplifier.
I think that's a really key insight for anyone listening. Nonlinearity isn't a bug, it's a feature. It's the whole goal.
It is the goal. Without the nonlinear switching of transistors, we couldn't create the ones and zeros of digital logic. The entire digital world is built on the failure of Ohm's law.
And it's not just semiconductors. You mentioned other things can fail linearity when you push them too hard.
Yeah, like a ferritic transformer. You drive it too hard, the magnetic core gets saturated.
What does that mean, saturated?
It just means the core can't hold any more magnetic flux.
Yeah.
And when that happens, the relationship between voltage and current goes completely nonlinear. You get all sorts of signal distortion.
And even a simple resistor can do this.
At extremes, yes.
Yeah.
At really, really high frequencies, tiny imperfections in the material start to matter. At really high voltages, it'll become nonlinear too, though usually it just burns up first.
So Ohm's law is a fantastic tool, but it's for a very specific job. For everything else, we need this universal language. So let's get into it. Kirchhoff's rules.
Let's do it.
Where do we start?
We start with his first rule, which is based on that idea you mentioned, conservation of charge. It's called the current law, or KCL.
Or the junction rule, I've heard it called that.
The junction rule, exactly. And it's very simple. It just says that the total amount of current flowing into a junction has to equal the total current flowing out.
A junction being any point where, 3 or more wires meet?
3 or more, yeah. We call it a node. And if you think about current as, a flow of electrons, it just makes sense.
Right. The electrons can't just vanish at a corner. They have to go somewhere.
They have to go somewhere. The node can't just store up charge or lose charge. What goes in must come out instantly. And that simple idea is the foundation for a whole method of analysis called nodal analysis.
Okay, so that's KCL. It handles the flow. It makes sure charge doesn't disappear. That brings us to the second rule, which is about energy.
Right, the loop rule, or Kirchhoff's voltage law, KVL.
KVL.
And this one says that if you start at any point in a circuit and you travel around in a closed loop, back to where you started, the sum of all the voltage changes must be 0.
So it's like hiking. You go up a mountain and back down to your starting point. Your net change in altitude is zero.
That's a perfect analogy. It's an energy accounting principle. All the energy that gets applied by sources, like your batteries, has to be used up by everything else in that loop. The resistors, the other components. Energy isn't created or destroyed in the loop.
So KCL is about charge, KVL is about energy. Why is it so important to use them together? Why can't I just keep using my simple series and parallel rules to simplify a circuit?
Because some circuits can't be simplified that way. If you have, say, two different batteries in different parts of the circuit that are both influencing the same component, you can't just combine things.
Or one of those bridge circuits, right?
Exactly. A bridge circuit is the classic example. There's no way to break it down into simple series or parallel chunks. KCL and KVL are the only systematic way to solve it.
So they turn the physical circuit diagram into a math problem.
Precisely. They let you generate a system of simultaneous linear equations, and once you have that, it's just algebra. We can solve for every single unknown current and voltage in that entire complex network.
Okay, so that's the strategy. It sounds a little intimidating, but you said it's systematic. Let's walk through that process.
It is very systematic. The first step is just labeling. You identify all your important nodes, and then you guess a direction for the current in every single wire.
Wait, you guess. What happens if I guess wrong? Does it ruin the whole thing?
Not at all. And that's the beauty of it. You make an assumption, you do the math, and if the final number for current comes out negative,
It just means the current is flowing the other way.
it's flowing the other way. The math corrects your initial guess. It's foolproof.
Okay, so we've labeled everything. We've guessed our directions. How do we start writing these equations without creating redundant ones?
Good question. For KCL, if you have, say, n nodes, you only write equations for n minus one of them. You leave one out, usually the ground or reference node, and that guarantees all your equations are independent.
And for KVL?
For KVL, you just identify every independent loop, every mesh, and you write one loop equation for each. You combine that with Ohm's law for the resistors, and boom, you have your system of equations.
And that system has the same number of equations as the number of things we don't know.
Exactly, which means it's solvable. And this whole process, this is literally the algorithm inside circuit simulation software, like SPICE.
So the computer's just doing this, but for thousands of nodes and loops at once.
That's all it is. It's building and solving a giant matrix based on KCL and KVL.
So once we've done the math and the computer has spit out some numbers, is there a way to check our work? A sanity check?
Yes, and it goes right back to the principle behind KVL, conservation of energy. The ultimate check is power balance.
Meaning?
The total power being supplied by all your sources, your batteries, your power supplies, must exactly equal the total power being consumed or dissipated by all the resistors and other components. If pin equals pout, you're golden. If not, you've got a mistake somewhere in your math.
That must be incredibly reassuring when you're designing something complex, knowing physics has your back.
It does.
Now, we talked about how all the interesting stuff happens with nonlinear components like transistors, but you just said Kirchhoff's laws generate linear equations. How do those two things work together?
Okay. So this is where we use a really clever technique called small signal analysis.
Small signal?
Right. So a transistor's full behavior is definitely nonlinear. The VI graph is a curve. But if we zoom in on a tiny, tiny piece of that curve, it looks almost like a straight line.
So we're basically lying to the math, but just a little bit.
Exactly. We're being very strategic liars. We pick an operating point,
Yeah.
a steady DC bias, and then we use a math trick, a Taylor series expansion, to pretend that just for small changes around that point, the device is linear.
And that lets you use all the standard tools again.
It lets us use KCL, KVL, and SPICE simulators to analyze amplifiers and other complex circuits. The results are only accurate for small signals, but it's an incredibly powerful approximation.
It's like forcing a complex reality into a simple box just long enough to get a useful answer.
It's a perfect way to put it.
Let's shift to some bigger real-world applications. How do these laws govern, say, power systems?
Well, KVL is fundamental to how we configure power sources. Think about batteries, if you connect them in series.
Like in a flashlight, end-to-end?
Exactly. KVL tells you that the voltages just add up. You get a higher total voltage. The current capacity, though, stays the same.
Okay. And what about in parallel, side by side? You see that in electric cars or solar panel arrays?
Right. In parallel, KVL dictates that the voltage has to be the same across all of them. But the real magic is what happens to the internal resistance of the batteries.
It goes down.
It goes way down because they're combined in parallel. And a lower overall internal resistance means the whole battery bank can deliver a much bigger current to the load without the voltage sagging. It's crucial for anything that needs a lot of power.
That's a great example. It shows how these aren't just abstract rules, they dictate fundamental design choices. But you said these laws rely on something called the lumped element model. We have to ask, where does that model break? Where do Kirchhoff's laws stop working?
The boundary is all about frequency and distance. The lumped element model assumes that all the electrical action happens inside the components and that the wires connecting them are just perfect instantaneous connections.
An assumption that can't be true forever.
No. When you get to really high frequencies, like gigahertz signals in a computer or a phone, the wavelength of the signal itself becomes comparable in size to the circuit board traces. The wires are no longer just wires.
And what does that do to the laws?
It breaks them. KCL, for instance, relies on charge being conserved at a node instantaneously. But at high speeds, the signal takes time to travel down the wire. You get capacitive effects between wires. The wire itself starts to store and release charge. So charge is no longer conserved right at the node boundary from one moment to the next.
So the flow isn't simple anymore? The pipes themselves start to leak and bulge, so to speak?
That's a good way to think about it.
Hmm.
And KVL fails for a similar reason with magnetism. KVL assumes that any changing magnetic fields are nicely contained inside components like inductors.
But they're not.
At high frequencies, they leak out, they radiate. Wires start acting like antennas. These stray fields transfer energy in ways the loop rule can't account for. At that point, you have to throw out Kirchhoff's laws.
And what do you use instead?
You have to move up to the next level of physics. Maxwell's equations. They describe the behavior of electric and magnetic fields everywhere, in time and space. They handle waves and radiation.
So if you're designing a power supply, Kirchhoff is your best friend. If you're designing a Wi-Fi antenna, you're in Maxwell's world.
That is the boundary, yes.
This has been a fantastic deep dive. It really puts everything in perspective. V equals IR is the simple case, the special tool. But the real operating system, the framework that makes all our complex technology possible, is Kirchhoff's systematic application of conservation laws.
It really is. And once you master that process of turning a physical circuit into that set of KCL and KVL equations, you've really unlocked the door to understanding almost any electrical network.
What's truly amazing, though, is how these ideas pop up elsewhere in science.
They're everywhere. This core concept of a potential driving a flow, it's not just electricity.
Right. You have voltage driving current, which is Ohm's law, but you also have a temperature difference driving a flow of heat,
Which is Fourier's law of heat conduction, or a pressure difference driving the flow of a fluid. It's all mathematically analogous. When you really get a handle on Kirchhoff's systematic way of conserving flow and energy, you've actually gained a tool to analyze all kinds of dynamic systems.
So you're saying the same kind of matrix math you'd use to solve a really complex circuit could also be used to model, what, a city's water supply system with pressure as the voltage and water flow as the current?
Mathematically, it's startlingly similar. The principles are universal. So the real challenge for you listening to this is to look around. What other complex systems, maybe even things like traffic patterns or financial flows, might start to make more sense if you try to apply the fundamental ideas of conservation that Kirchhoff first laid out for us in a circuit.